In this video we're going to be continuing with our analysis of mathematical induction, and this time we're going to be looking at combinatorial proofs, and we've got to use mathematical induction to prove this, which is actually quite a common exam question, so it's well worth getting to grips with. Okay, just a couple of things before we start. Basically what this means, the sum from r equals 0 to n of nr equals 2 to the n, that's basically the sum n0 add n1 add n2 add n minus 1 add n. And another way that might be written is nr. Some people don't use this notation. It also can be written as ncr. So basically if you have ncr here instead of nr, it's exactly the same question, and that equals, either way, it equals n factorial over r factorial n minus r factorial. So basically those three things are exactly the same thing. Okay, now what we're actually proving here is quite interesting. Just as a little side note, if we look at Pascal's triangle, 1 1 1 1 2 1 1 3 3 1 1 4 6 4 1, and then we add them up, well, that equals 1, that is 2, that is 4, that is 8, and that is 16, etc, etc, etc. Well, that is 2 to the 0, that's 2 to the 1, that's 2 squared, that's 2 cubed, and that's 2 to the 4. So that is what we are actually proving in this proof by induction. Okay, so let's get on with the proof. What we need to do is, as usual, there are 4 bits. First of all, we need to show that it's true for the base case, and in this particular question it asks us, it says the base case n greater than or equal to 0, so our base case is n equals 0. Then what we do is we assume true for n equals k. Then C, we have to show that it's true for n equals k plus 1, and then D, to get our final mark, we have to write our conclusion in the correct form. Okay, so let's get going. Right, let's do the base case first. The base case is basically the sum, so this is A, the sum between 0 and r equals 0 of nr equals the sum, well, 0 r equals 0 of 0 0, which by our definition is 0 factorial over 0 factorial 0 factorial, which equals 1. 0 factorial is 1, and 2 to the power of 0 equals 1 as well. So therefore the sum is equal to 2 to the power of n for n equals 0, and therefore we've proved our base case. Okay, so now what we've got to do is prove our assume true for n equals k, and therefore we assume that the sum between r equals 0 and k of kr equals 2 to the k, which equals k0 add k1 add add k. So that's basically what we are assuming to be true. C, we need to show, therefore, that it's true for n equals k plus 1, i.e. we need to show that it is true for r equals 0 to k plus 1, k plus 1 r equals 2 to the k plus 1. All I've done there is I've replaced the k with k plus 1. So that's what we have to show is true, and just expanding that is basically k plus 1 0 add k plus 1 1 add add k plus 1 k plus 1. That is what we are trying to do there. Now what we're going to do to show this is we're going to use Pascal's identity, which I will prove at the end, but which you can just quote in this proof. And Pascal's identity says that n plus 1 p equals n p minus 1 add n p. That's what Pascal's identity says. And again, like I say at the end of this video, for those so interested, I will prove how we know that is correct. Okay, so moving back to our here we have k plus 1 0, whoops, sorry, my bad, k plus 1 0 add k plus 1 1 add k plus 1 2 add add k plus 1 k, oh, my apologies, add k plus 1 k plus 1. That's basically what we're looking to sum. Okay, so let's leave this bit here. That's k plus 1 0 add. Okay, now k plus 1, 1, let's use Pascal's identity here to split this one into, using this formula here, we can split it into k0 add k1. All I've done is I've used this identity here, where k is the n and p is 1. Okay, and then let's split this one as well by Pascal's identity, and that will give us k1 add k2. And then let's go all the way over here and let's split this one here again by Pascal's identity. That will give us add k minus 1, add k by Pascal's identity there, and then finally we're just left with this last one, add k plus 1, k plus 1. Okay, now if we just look at this one, anything n0 is basically just equal to 1 by definition, so we could rewrite k plus 1, 0 as k0, and ditto k plus 1 is equal to 1 as well. That basically equals 1, and so we could rewrite that one as kk, so that's basically that. Now if we look and rewrite all of this bit in the middle, we have k plus 0, add k plus 0, k0, add k1, add k1, add k2, add k minus 1, add kk, add kk. And if you notice, we have 2 of each of these, and therefore we can take the factor of 2 out, and that gives us 2 k0 add k1 add k2 add k. And going all the way back to our assumption is that k0 add k1 add kk is equal to 2 to the k. So we can replace this by 2 to the k, so that equals 2 times 2 to the k, which is 2 to the k plus 1 as required. So therefore we have done our part C, and all we need to do now, as required, and all we need to do now is just write our conclusion, which is part D, which is, as it's true for base case n equals 0, and as it's true for n equals k plus 1, given true for n equals k, then we have proved correct the statement by mathematical induction, and that gets us our extra mark. Okay, so that's that done. Now, just a couple of other points. Anybody who's only interested in the conclusion, there, that's finished now, so that's all done. A couple of other things, anybody who is interested, there is another way that we can prove this, which is quite neat, actually. If we just look at the binomial expansion, 1 plus x to the n, well, that equals basically the sum between r equals 0 and n of nr x to the r, which is 1 add nx add n minus 1 over 2 factorial x squared add add x to the n. And then if we just let x equal 1, we have 1 add 1 to the n equals the sum between r equals 0 and n of 1 add n times 1 add n minus 1 over 2 factorial times 1 add 1. And that lot there is basically equal to the sum between r equals 0 and n of nr times 1 to the r, which of course equals the sum between r equals 0 and n of nr, because 1 to the power of anything is just 1. So that's just another way, a nice little neat way of proving with an alternative method. And finally, as promised, I did say that we would prove Pascal's identity. So we had Pascal's identity, which was n plus 1p equals np minus 1 add np. Okay, well, using our definition of n plus 1p, n plus 1p equals n plus 1 factorial over p factorial n plus 1 minus p factorial. So we have to prove that this right hand side is also equal to that. So let's have a look at the right hand side. So n p minus 1 add np equals n factorial over p minus 1 factorial n minus p minus 1 factorial add n factorial over p factorial n minus p factorial, and that equals n factorial. Let's multiply top and bottom here by p, and that will give us here p factorial, n factorial p over p factorial n plus 1 minus p factorial add, and on this top hand here, let's multiply top and bottom by n minus p plus 1, and that will give us n factorial n minus p plus 1 over p factorial, and n minus p factorial times n minus p plus 1 gives us n minus p plus 1 factorial. And then basically all we need to do now is just expand all of this. That equals n factorial p over p factorial n plus 1 minus p factorial add. Now here we have n plus 1, so n plus 1 times n factorial is n plus 1 factorial over p factorial n plus n minus p plus 1 factorial minus n factorial p over p factorial n minus p plus 1 factorial, and this cancels with this, leaving us with n plus 1 factorial over p factorial n minus p plus 1, which equals n plus 1 p, as we showed here. It's exactly the same thing. Okay, so they are basically just a little couple of asides. So going back to the original question, that's how you do it, by induction. If you found this useful, then please like this video and subscribe to the Gresti Academy YouTube channel. Thank you.